Hello, in this lecture we'll answer on two questions. In the first question we'll find out the radius of this circle that is inscribed by the right triangle, triangle ABC. And in the second question we'll find out the area of the blue right triangle, triangle DCB that is inscribed by the quarter circle. We'll start with the first question. In the first question, we have the right triangle, triangle ABC. We know that side AB equals to 8 units, angle ABC equals to 90 degrees. And inside this right, and you also know that the length of side BC and side AC are integers. The lengths are integers. Inside this right triangle, triangle ABC, we have this circle. So this circle is described by triangle ABC, and we want to find out the radius of this circle. So first of all, we define side BC as A. And we will define side AC, the hypotenuse AC, as B. And then we will implement the Pythagoras theorem on the right triangle, triangle ABC. So on the right triangle, triangle ABC, by PT is the relation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC square equals to AB square plus BC square. I'll repeat again. The right triangle, triangle ABC. According to the Pythagoras theorem, AC square equals to AB square plus BC square. According to our definition, AC equals to B, therefore AC square is B square. And it is equal to AB square. AB is 8, so AB square is 8 squared, that is 64. Plus BC square. BC equals to A according to our definition, therefore BC square is A square. So in conclusion, according to equation number 1, we found out that B square equals to 64 plus A square. We subtract B square from this equation number 1, and we'll subtract actually A square from this equation number 1, and we get that according to equation number 1, B square minus A square equals to 64. We have the algebraic identity that B square minus A square, it is equal to B plus A times B minus A. So we substituted B square by A square by B plus A times B minus A. And according to equation number 1, it is equal to 64. Okay, so actually it is given us the question that AC and BC are integers. But according to our definition, AC equals to B and BC equals to A, so you can write down that A and B are integers according to what is given as the question. And in addition, we also know that A and B are the lengths of the sides of the right triangle, triangle ABC. So A and B, they are lengths, and as the lengths, they must be positive numbers. So actually from 1 and 2 we get that A and B, they are actually positive integers. A and B, they are positive integers, and actually B is a positive integer and A is a positive integer, therefore B plus A must be also positive integer. Because when you add two positive integers to each other, the result must be a positive integer. So B plus A is a positive integer, and actually this positive integer B plus A, when you add the two positive integers together, it must be greater than the case that you subtract the two positive integers from each other. That is to say, B plus A is greater than B minus A. Okay, it is very simple and logic and obvious that when you add two positive integers together, they must be greater than the case that you subtract the two positive integers from each other. So B plus A is greater than B minus A, and we also know that B is the hypotenuse of the right triangle, and the hypotenuse is greater than any side of the triangle, so B is greater than A. We subtract A from this equation, from this inequality, and we get that B minus A is greater than 0. That is to say, B minus A is a positive number. But because of the fact that B is a positive integer and A is a positive integer, it means that if B minus A is a positive, it must be a positive integer. That is to say, here B minus A is a positive integer. Okay? Actually, in the world of the positive integers, if you are in this world, then if you add two numbers together, you must remain in this world of positive integers. And the same thing is true when in the case that you subtract two positive integers from each other. If the result is not a negative but a positive number, it must be a positive integer. We are not talking about the case that if A equals to B, of course the B minus A will be equal to 0, but if B is not equal to A, then we know that B minus A is a positive number, then B minus A must be a positive integer. Okay? Actually, here it is impossible that B equals to A, because if B equals to A, then we get that in equation number 1, B minus A is 0, and 0 times anything is 0. But according to equation number 1, B plus A times B minus A is not a 0, but 64. Therefore, for sure, here B is not doesn't equal to A. Okay? Therefore, if B minus A is a positive number, it must be a positive integer. So actually, according to equation number 1, when we multiply b plus a, that is a positive integer, by b minus a, that is also a positive integer, the result is 64. In the next step, we will write down all the possibilities that when you multiply two positive integers by each other and the result is 64. Actually, there are not a lot of possibilities here. Okay, so we write down all the options that you multiply two positive integers by each other and the result is 64. Okay. The first option is that b plus a is 1, b minus a is 64. The second option is b plus a is 2 and b minus a is 32. The third option is b plus a is 4 and b minus a is 16. The fifth option is that b plus a is 8 and b minus a is 8 also. The fifth option is that b plus a equals to 16 while b minus a equals to 4. The sixth option is b plus a is 32 while b minus a is 2, and the last option is that b plus a is 64 while b minus a is 1. So those are the possibilities that we have, that we multiply two positive integers by each other, the result is 64. But here, according to what we have already found out, we know that b plus a is greater than b minus a. So all the numbers in this column, in the first column, are b plus a, and all the numbers in the second column is b minus a. And we know that b plus a is greater than b minus a, that is to say, the first column must be greater than the second column. And if we found here that the first column is not greater than the second column, we'll cancel this solution, this option, because according to what we have already found out, b plus a must be greater than b minus a. So here 1 is not greater than 64, therefore we'll cancel this option. 2 is not greater than 32, therefore we will cancel this option. 4 is not greater than 16, therefore we will cancel this option. 8 is not greater than 8, therefore we will cancel this option. Here 16 is greater than 4, this is a valid option. 32 is also greater than 2, this is a good option. And in the end we have 64 that is greater than 1, that is to say it is a good option. So we have three options for b plus a and b minus a. Okay, in the next step we will add b plus a to b minus a in order to find out the result. And from this result we also eliminate one of the three options that is left for us. Only those three options are left as a possible answer to the question. Okay, so here we will add equation number 1 to equation number 2. We will add b plus a to b minus a, and we will get that here b plus b is 2b and a minus a is 0. In conclusion, we found out that when we add the two numbers together, that is to say b plus a plus b minus a, we got here an even number. B is a positive integer, therefore 2b must be an even number. 2b is even number, that is to say, now we will check all the options that we have. We will add the first number to the second number, and if the result gives us an even number, it is a good option. Otherwise, if it is not an even number, we'll cancel this option, because when you add the two numbers together, the result must be a positive number. So here 16 plus 4 is 20. 20 is an even number, therefore this is a good option. We have also 32 plus 2 is 34. 34 is an even number, that is also a good option. And finally 64 plus 1 is 65, that is an odd number, it is not an even number, therefore this is not an option that can be the answer to our question, because according to what we have already found out, if we add the two numbers together, the result must be an even number. So we left only with two options that are left for b plus a and b minus a. So copy the two options, and in the next step we will find out the values of a and b in each option. So here we have according to the first option, b plus a equals to 16, while b minus a equals to 4. And according to the second option that we have here, we found out that b plus a equals to 32, while b minus a equals to 2. We'll focus on the first option, and we will add the first equation to the second equation. In this way we'll find out the value of b, and then we'll find out the value of a from this equation. So here b plus b is 2b, and a minus a is 0. So in this side of the equation we have 2b, in the other side of the equation we have 16 plus 4, that is 20. So in conclusion, we found out that 2b equals to 20. Here we'll divide this equation by 2, and we'll get that according to this equation, b equals to 20 over 2, that is 10. We found out that the hypotenuse b of the right triangle ABC equals to 10 units. Now we have the equation that b plus a is 16. Here we subtract b from this equation, and we get that a equals to 16 minus b. Okay, a equals to 16 minus b, that is to say a equals to 16 and b is 10, so it is 16 minus 10. 16 minus 10 is 6, so in conclusion we found out that a equals to 6. A equals to 6 units. That is the perpendicular of the right triangle ABC. That is A, it is equal to 6 units. And the perpendicular and the hypotenuse B, it is equal to 10 units. This is the first option for the values of the sides of the right triangle ABC. And the second option here, it is the second option, so we will add equation number 1 to equation number 2, and we get that b plus b is 2b. A minus a is 0, so in this side of the equation we have 2b, and the other side of the equation we have 32 plus 2 is 34. Here we will divide this equation by 2, and we will get that b equals to 32 over 2 is 17. So we found out that the hypotenuse b equals to 17 units. Here we have the equation that b plus a equals to 32. We'll subtract b from this equation and we'll get that a equals to 32 minus b. That is to say a equals to 32 and b is 17. So it is 32 minus 17. That is to say a equals to 15 units and b, the hypotenuse b, equals to 17 units. In the next step, I will draw the two right triangles here. So we have the first right triangle, triangle ABC. We have here, this is the right triangle, triangle ABC. We know that side AB equals to 8 units, it's given us in the question. Side BC equals to 6 units. And the hypotenuse AC equals to 10 units. Actually, inside these specific right triangles, we have this circle, and we are looking for the radius of this circle that is inscribed by the right triangle, triangle ABC. Okay, so we define the radius of this circle as capital R, and we are looking for the value of capital R. So this is the first triangle, the first right triangle that is possible for the solution to the question, but we have to find out the radius of this circle that is described by this specific right triangle, triangle ABC. And the second solution to the question will be the second option here. Here we have this is the right triangle, triangle ABC. We know that AB equals to 8 units, it is given as the question. We have already found out that BC equals to 15 units and the hypotenuse AC equals to 17 units. Inside this right triangle, triangle ABC, we have this circle, and we are looking for the radius of this circle that is described by the right triangle, triangle ABC. So we define the radius as capital R, and our mission is to find out the radii of the two right triangles. So the radii of two right triangles that blocking the two circles inside them. Okay, so in order to find out the radius of each circle, we will take a right triangle, triangle ABC, that could be any triangle, and we will find out the radius of this circle that is inscribed by this right triangle, triangle ABC, that could be any triangle. And by finding the radius of this circle, so we have here a right triangle ABC. Inside this right triangle we have this circle, and when we will find out the radius of this circle, we can use the formula that we will find out for finding out the radius of the circles that are inscribed by our triangles. So we start with the mission. We define side AB as A. Here AB equals to A according to our definition. We define side BC as B. So BC equals to B according to our definition. And we define side AC, the hypotenuse AC is C. That is to say, AC equals to C according to our definition. In the next step, we define the center of this circle as O. We define the point of tendency of tangent AB with this circle as N. We define the point of tendency of tangent BC with this circle as M. We define the point of tendency of tangent AC with this circle as L. In the next step, we join points O and N together by a straight line. Here, what is the definition of line segment ON? Point O is the center of the circle. Point N is the point of the circle itself. This is exactly the definition of a radius. That is to say, NO is the radius of the circle that is equal to capital R according to our definition. Here we have rule number 1 that states that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here we have the radius ON that is drawn to the point of tendency, that is to say, it is drawn to point N, that is the point of tendency of tangent AB with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. So if AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Likewise, we have the radius OM that is drawn to the point of tendency. Therefore, according to rule number 1, tangent BC will be perpendicular to the radius MO. So if BC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Actually, we have here quadrilateral NOBM that has 3 right angles, 1, 2, 3, and the sum of 3 right angles is 90 times 3 is 270 degrees, plus the 4th angle that is actually angle NOM, this angle. In total, the sum of those 4 angles must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So if we subtract 270 degrees from the equation, we get that the missing angle NOM is equal to 90 degrees. So we found out that inside quadrilateral NOBM we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral NOBM as a rectangle, and you know that the opposite sides of a rectangle are equal to each other. That is to say, NO equals to BM. So NO equals to BM, but we have already found out that NO equals to R. Therefore, BM that is equal to NO must be also equal to R. Okay, likewise, according to the rule that the opposite sides of a rectangle are equal to each other, we get that NB equals to OM. NB equals to OM, but we have already found out that OM equals to R, and NB equals to OM. Therefore, NB must be also equal to R. So in conclusion, quadrilateral NOBM, it is not a rectangle, but a square. Because all of its sides, they are equal to each other, they are equal to capital R. In the next step, we find out the length of line segment AN. AN equals to AB minus BN. Again, AB minus NB equals to AN. That is to say, AB equals to AN equals to AB, that is A, minus NB, that is R. So in conclusion, AN equals to A minus R. Here we find out the length of line segment MC. MC equals to BC minus BM. BC minus BM equals to MC, that is to say MC equals to BC, that is B, minus BM, that is R. So B minus R equals to MC. In the next step I will present to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. So here, if we focus on the common external point, point A, we have tangent AN and tangent AL. And according to rule number 2, they must be equal to each other. That is to say, AN equals to AL. But according to rule number, okay, AN equals to AL, but we have already found out that AN equals to A minus R. Therefore, AL that is equal to AN must be also equal to A minus R. In the next step, we'll focus on the common external point, point C. From the common external point, point C, we have two tangents to this circle, tangent CM and tangent CL. And according to rule number 2, they are equal to each other. That is to say, CL equals to CM. But we have already found out that CM equals to B minus R, and CL equals to CM. Therefore, CL must be also equal to B minus R. In conclusion, we found out that CL equals to B minus R, and AN equals to A minus R. So what is the length of the hypotenuse AC? The hypotenuse AC it will be equal to the hypotenuse AC. From the drawing, it is very easy to see that AC equals to AL plus LC. AL plus LC equals to LC. Again, AC equals to AL plus LC. AC equals to AL plus LC. That is to say, AC equals to C according to our definition. AL equals to A minus R. We substitute AL by A minus R plus LC. LC equals to B minus R. So in conclusion, we found out that C equals to A minus R plus B minus R. That is to say, C equals to A plus B, and minus R plus minus R is minus 2R. Okay, C equals to A plus B minus 2R. We'll add 2R to this equation, and we'll get that 2R plus C equals to A plus B. Here we subtract C from this equation, and we get that 2R equals to A plus B minus C. We divide this equation by 2, and we get that the radius that we are looking for, it is equal to A plus B minus C over 2. Okay, the radius equals to A plus B minus C over 2. So now we found a general formula to find out the radius of a circle that is inscribed by any right triangle. By any right triangle, it includes also our two right triangles. So we use this formula in order to find out the radii of the two right triangles that are inscribed in the radii of the two circles that are inscribed into those two right triangles. Okay, so here I'll copy the new formula. According to the new formula, R equals to A plus B minus C over 2. Okay, this formula is true for any right triangle that includes also those two right triangles. So here in this right triangle we'll get that R, the radius of this circle, equals to A plus B, that is the sum of its perpendiculars, that is 8 plus 6, minus the hypotenuse, that is 10 over 2. So here 8 plus 6 is 14, 14 minus 10 over 2, 14 minus 10 is 4, and 4 over 2 is 2. So I found out that the radius of this circle that is described by this specific right triangle, triangle ABC, equals to 2 units. So here R equals to 2 units. And we also have the second right triangle, triangle ABC. We use the same formula to find out the radius of this triangle that is described by this right triangle. So here the radius of this circle that is described by this right triangle will be equal to A plus B. A is 8, B is 15, minus the hypotenuse, that is 17 over 2. 8 plus 15 is 23, and 23 minus 17 over 2. 23 minus 17 is 6, and 6 over 2 is 3. So I found out that the radius of this circle that is described by this specific triangle, triangle ABC, equals to 3 units. So in conclusion, we have two solutions that are possible for this question. Here, the radius of this circle that is described by this specific triangle, triangle ABC, equals to either 2 units or 3 units. Okay, so we can write down here that the radius of the circle that is described by the right triangle, triangle ABC, equals to either 2 units or 3 units. And that is the answer to the question. In the next step, I'll present to you the second question, and we'll solve the second question in 2 different methods. Okay. In the drawing, we have a quarter circle A or B. Side BO equals to 2 units, AD equals to DO. Inside this quarter circle, we have the right blue triangle, triangle BCD, and DCB equals to 90 degrees. And we want to find out the area of this right blue triangle, triangle DCB. So we'll start with the first method. Because of the fact that AOB is a quarter circle, then angle AOB must be equal to 90 degrees. Angle AOB equals to 90 degrees. Point O here is the center of the quarter circle. OB is the radius of this quarter circle that is equal to 2 units according to what is given us. AO is also the radius of the quarter circle, therefore it is also equal to 2 units. So we can write down here that AO, from the drawing it is easy to see that AO equals to AD plus DO. AD plus DO, but because of the fact that AD equals to DO, if we define AD as X, then DO also equals to X. Therefore, we can write down that AD that is X plus DO that is also X equals to AO that is equal to OB, that is actually the radius of the quarter circle, that is equal to 2 units according to what is given as the question. X plus X is 2X. 2x equals to 2. We divide this equation by 2 and we get that x equals to 1. Okay, x equals to 1. That is to say AD that is equal to x equals to 1 unit, that is also equals to x equals to 1 unit. And here we will complete the quarter circle to a circle. Here we completed the quarter circle to a circle. The next step, we will extend the radius BO by a straight line until it touches the circle. At this point, we will define the touching point of the extended BO and the circle as point P. So here, point O is the center of the circle. Point P is the point of the circle itself. This is exactly the definition of a radius. That is to say, PO is the radius of this circle that is equal to 2 units according to what is given as the equation, because the radius of the circle is the sum of the radius of the quarter circle. They have the same radius. In the next step, we will extend side CD of the right triangle DCB by a straight line until it touches the circle. We actually don't know where the extended side CD will touch the circle. Therefore, we will assume that the touching point of the extended CD and the circle will be at point X. Not at point P, but at point X. Okay? According to our assumption, the extended side CD will touch the circle at point X. That is obviously not point P. Therefore, actually, we created here peripheral angle BCX. We created peripheral angle BCX, and according to what is given as the question, peripheral angle BCX equals to 90 degrees. Okay? Peripheral angle BCX equals to 90 degrees according to what is given as the question. But because of the fact that we have the rule that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle, here PB is the diameter of this circle. Why PB is the diameter of the circle? Because of the fact that line segment PB passes through point O, that is the center of the circle. Actually, we extended the radius BO by a straight line, therefore the result BP must be also a straight line, because when you extend a straight line by a straight line, the result must be a straight line. So, first of all, BP is a straight line. Therefore, BP is also a chord. Chord BP passes through point O, that is the center of the circle. Therefore, chord BP is the diameter of the circle. Okay? I repeat again that according to the rule that I mentioned, here peripheral angle BCP, because of the fact that it is equal to 90 degrees, it must rest on PB, that is the diameter of the circle, because any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. But according to our assumption, angle BCX doesn't rest on the diameter, that is PB. So we have here a contradiction. The contradiction is that we created here peripheral angle that is equal to 90 degrees and it doesn't rest on the diameter of the circle, that is the contradiction to the rule that any peripheral angle that is equal to 90 degrees must rest on the diameter. So this angle must rest on PB. But here, if this peripheral angle is BCX, it doesn't rest on the diameter that is PB. In order to avoid the contradiction, point X must merge with point P. And in this way, we will get here peripheral angle BCP, and this peripheral angle BCP this peripheral angle BCP that is equal to 90 degrees indeed rests on the diameter of the circle that is PB. Okay? Therefore, point X merge with point P, and we have here peripheral angle BCP that is equal to 90 degrees that is resting on the diameter of this circle that is PB. In this way, we doesn't have a contradiction anymore. Okay? So here, PB is the diameter of the circle, therefore it is absolutely a straight line. And we know that the sum of the angles on one side of the straight line equals to 180 degrees. So if we focus on the upper side of the straight line PB at point O, here the sum of the angles must be equal to 180 degrees. Which angles we have on the upper side of PB at point O? We have 90 degrees plus angle AOP. In total, the sum of those two angles must be equal to 180 degrees. So 90 degrees plus angle AOP equals to 180 degrees. If we subtract 90 degrees from the equation, we get that the missing angle AOP, also equals to 90 degrees. So this angle is right angle, it is equal to 90 degrees. So we have here triangle POD is a right angle because it has one angle that is equal to 90 degrees. We will find out the length of the hypotenuse PD by implementing the Pythagoras theorem on the right triangle, triangle POD. According to the Pythagoras theorem on the right triangle, triangle POD, the sum of the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here by PT is the information of Pythagoras theorem. So the square of the hypotenuse is PD square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to DO square plus PO square. Okay, I'll repeat again. In the right triangle, triangle POD, PD square equals to DO square plus PO square. So PD square equals to DO square. DO is 1, so DO square is 1 square, that is 1, plus PO square. PO is 2, so PO square is 2 square, that is 4. So we found out that PD square equals to 1 plus 4, that is 5. We take out of this equation, we find out that PD equals to the square root of 5 units. So we found out that PD equals to the square root of 5 units. Here PD equals to the square root of 5 units. We repeat on the same process on the right triangle, triangle DOB. We'll find out the value of the hypotenuse DB by implementing the Pythagoras theorem on this right triangle, triangle DOB. Okay, so according to the Pythagoras theorem, in the right triangle, triangle DOB, this right triangle, by PT is the relation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say DB square equals to DO square plus OB square. I repeat again, in the right triangle DOB, according to the Pythagoras theorem, DB square equals to DO square plus OB square. So DB square, the square of the hypotenuse, equals to DO square. DO is 1, so DO square is 1 square, that is 1, plus OB square. OB is 2, so OB square is 2 square, that is 4. So in conclusion, we found out that dB square equals to 1 plus 4, that is 5. Here we take out of this equation and we will find out that dB equals to the square root of 5 units. Here dB is also equals to the square root of 5 units. In the next step, we will extend the radius AO by a straight line until it touches the circle. At this point, we define the touching point of the extended AO in this circle as point Z, and we'll implement rule number 1 here that talks about two chords that intersect with each other inside a circle. Okay? So here, if we have this circle, inside this circle we have chord AB. This is called AB, that intersects with chord CD. This is called CD. And the intersection point is at point O. So if chord AB intersects with chord CD at point O, then the following equation is true. That AO times OB equals to CO times OD. Repeat again, AO times OB equals to CO times OD. Okay, we can implement rule number 1 in our drawing, because in our drawing we have chord AZ intersects with chord CP at point D. I'll repeat again, chord AD intersects with chord CP at point D. Therefore, according to rule number 1, we'll get that AD times DZ equals to CD times DP. Repeat again, chord AZ intersects with chord CP at point D, therefore according to rule number 1, we'll get that AD times DZ equals to CD times DP. Okay? So here, AD equals to 1 unit, DZ, what is the value of DZ? Here we know that point O is the center of the circle, point Z is the point of the circle itself. This is exactly the definition of a radius. That is to say, OZ is the radius of this circle, that is equal to 2 units. So, the length of line segment DZ is 1 plus 2, that is 3. So dz equals to 3 units, and it is equal to CD. CD is the missing line segment, so we leave it as it is, times dp. dp equals to square root of 5 units. So in conclusion, we found out that square root of that 3 equals to square root of 5 times CD. We'll divide this equation by square root of 5, and we'll get that the missing line segment CD, it is actually equals to 3 over square root of 5 units. So here we found out that CD equals to 3 over square root of 5 units. In the next step, we will implement the Pythagoras theorem on the right blue triangle, triangle CDB. On the right blue triangle, triangle CDB, by PT is the relation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say, dB squared equals to CD squared plus CB squared. I repeat again, in the right triangle, triangle CDB, according to the Pythagoras theorem, dB squared equals to CD squared plus CB squared. Here, dB equals to square root of 5 units, so dB squared is square root of 5 squared, that is 5, and it is equal to CD squared. CD equals to 3 over square root of 5, so CD squared is 9 over 5, plus CB squared, that is missing 9 segments, so we leave it as it is. So in conclusion, we found out that 5 equals to 9 fifths plus CB squared. We'll subtract 9 fifths from this equation, and we get that 5 minus 9 fifths equals to CB squared. Here we'll multiply 5 by 5, and then we'll divide it by 5 in order to have a common factor with this expression. 5 times 5 is 25, minus 9 over 5 equals to CB squared. So here 25 minus 9 is 16. So we have 16 over 5 that is equal to CB squared. Here we take a root out of this equation, and we get that the missing line segment CB, it is actually equals to square root of 16 is 4 over square root of 5. So we found out that the length of line segment CB equals to 4 over square root of 5 units. Now it is very easy to find out the area of the blue right triangle, triangle DCB, the area of the right triangle, triangle DCB, the right blue triangle, triangle DCB, will be equal to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. Okay, the area of the right triangle, triangle DCB equals to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. So here DC equals to 3 over square root of 5, CB equals to 4 over square root of 5, all divided by 2. So in conclusion, we found out that we have here in the numerator 3 times 4 is 12. In the denominator we have square root of 5 times square root of 5 is 5, times 2. Here 12 over 2 is 6, so in the numerator we left only with 6, and in the denominator we left only with 5. So here the right triangle DCB equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. Okay, so we finished with the first method. In the next step I will present to you the second method. Actually here, according to the first method, angle A or B equals to 90 degrees. Point O is the center of the quarter circle. AD equals to 1 unit, DO equals to 1 unit. We'll complete the quarter circle to a semicircle. then we'll extend the radius OB by a straight line until it touches the semicircle. This point P. Point P is the touching point of the extended radius BO and the semicircle. Point O is the center of the semicircle. Point P is the point of the semicircle itself. This is exactly the definition of a radius. That is to say, PO is the radius of the semicircle that is equal to 2, because the radius of the semicircle is the same radius of the quarter circle. Okay? The radius of the quarter circle equals to 2 units, therefore the radius of the semicircle PO also equals to 2 units. Okay? Here, in the next step, we will extend side CD by a straight line until it touches the circle. And according to method 1, we have already proved that if we extend side CD by a straight line, it must touch the circle of the semicircle at point P and only at point P. Therefore, when we extend side CD, it will touch the circle the semicircle at point P. Okay, according to the first method, we will define angle DOP as theta. According to the first method, angle DOP equals to 90 degrees. It is a right angle. So actually inside right triangle DPO, we have this angle that is equal to theta. This angle equals to 90 degrees, therefore the third angle, the missing third angle, must be equal to 90 degrees minus theta. In order to complete the sum of the angles in this right triangle DOP to 180 degrees, this angle must be equal to 90 degrees minus theta, because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. And exactly for the same reason, if you focus on the right triangle BCP, this angle equals to theta, this angle equals to 90 degrees, so this angle must be equal to 90 degrees minus theta, exactly for the same reason. In the next step, we will prove that the right triangle POD is similar to the right triangle PCB. So write it down. The right triangle POD is similar to the right triangle PCB. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So this angle that is actually angle POD equals to this angle that is actually angle PCB, and they are both equal to 90 degrees, therefore they are equal to each other. I repeat again, angle POD equals to angle PCB, and they are both equal to 90 degrees. In addition, we have those two angles that are both equal to 90 degrees minus theta, therefore they are equal to each other. So this angle that is angle PDO equals to this angle that is angle PBC, and both angles are equal to 90 degrees minus theta, therefore they are equal to each other. And repeat again, angle POD equals to angle PBC, and they are both equal to 90 degrees minus theta. And finally, we have this angle that is a common angle, it belongs to both triangles. So this angle equals to itself. So we can write down that angle DPO equals to itself, that is actually can represent it as angle CPB, and they are both equal to 90 it is equal actually to theta according to our definition. So I repeat again, angle DPO equals to itself. We can represent it also as angle CP, and it is equal to theta according to our definition. This is to say it is a common angle that belongs to both triangles. So this angle equals to itself. Actually, we proved that all three angles of triangle POD can go into all three angles of triangle PBC, therefore triangle POD is similar, this is the sign of similar, to triangle PCB according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that PD over PB equals to DO over CB, and it is also equals to PO over PC. I'll repeat again. Because of the fact that the two right triangles are similar to each other, we conclude that PD over PB equals to DO over CB, and it is also equals to PO over PC. Here. Actually, according to the first method, the hypotenuse PD equals to the square root of 5 units, and we already found out in the first method that the hypotenuse DB in the right triangle DOB also equals to square root of 5 units. Okay? So actually, here, PD equals to the square root of 5 units, according to the first method. PB equals to 2 plus 2, that is 4, and it is equals to DO. DO is 1 over CB is the missing line segment, so we will leave it as it is, and it is equal to PO. PO is 2 over PC. PC equals to square root of 5 plus DC. So actually, in conclusion, we found out that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Here, from this long equation, we derive the first equation, that square root of 5 over 4 equals to 1 over CB. Here we will cross multiply this equation number 1, and we get that according to equation number 1, the square root of 5 times CB equals to 4. Here we divide this equation number 1 by square root of 5, and we get that according to equation number 1, the missing line segment CB equals to 4 over square root of 5 units. Here CB equals to 4 over square root of 5 units. In the next step, we will implement the Pythagoras theorem on the right blue triangle, triangle DCB. According to the Pythagoras theorem on the right blue triangle, triangle DCB, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, by PT, so the square of the hypotenuse is dB squared equals to DC squared plus CB squared. I'll repeat again. According to the Pythagoras theorem, in the right triangle DCB, dB squared equals to DC squared plus CB squared. So here dB is square root of 5 units, so dB squared is square root of 5 squared, that is 5. That is equal to DC squared. DC is the missing line segment, so we leave it as it is. DC squared plus CB squared. CB is 4 over square root of 5. Therefore CB squared is 16 over 5. So in conclusion, we found out that five equals to DC squared plus 16 fifths. We subtract 16 fifths from this equation, and we get that 5 minus 16 fifths equals to DC squared. Here we will multiply 5 by 5 and then we divide it by 5 in order to have a common factor with this expression. 5 times 5 is 25 minus 16 over 5 equals to DC squared. So here 25 minus 16 equals to 9, and 9 over 5 equals to DC squared. Here we take a root out of this equation and we'll get that according to this equation DC equals to the square root of 9, that is 3, over square root of 5. So DC equals to 3 over square root of 5. You can write here that DC equals to 3 over square root of 5. Now it is very easy to find out the area of the blue right triangle, triangle DCB. The area of the blue right triangle, triangle DCB will be equal to the base of the triangle, that is DC, times the height of the base, that is CB, over 2. I repeat again, the area of the blue right triangle, triangle DCB equals to the base of the triangle, that is DC, times the height of the base, that is CB, over 2. So here, DC equals to 3 over square root of 5 units, times CB, that is 4 over square root of 5 units, all divided by 2. So here we have, in the numerator of 3 times 4 is 12. In the denominator we have square root of 5 times square root of 5, that is 5, times 2. So 12 over 2 is 6. In the numerator we have 6 only. In the denominator we left only with 5. So in conclusion, we found out that the area of the right blue triangle, triangle DCB equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. In the next step I will summarize the lecture. We start with the first question, of course. So, in the drawing, we have the right triangle, triangle ABC, side AB equals to 8 units, angle ABC equals to 90 degrees. We know that the length of side BC and side AC, the lengths are integers. Inside this right triangle, triangle ABC, we have this circle that is described by the right triangle ABC, and we want to find out the radius of this circle that is described by triangle ABC. So first of all, we defined side BC as A and side AC, the hypotenuse, as B. Then we implemented the Pythagoras theorem on the right triangle, triangle ABC. According to the Pythagoras theorem on the right triangle, triangle ABC, AC squared equals to AB squared plus BC squared, AC squared equals to AB squared plus BC squared. AC equals to B according to our definition, so AC squared is B squared. AB is 8, so AB squared is 8 squared, that is 64, plus BC squared. BC is A, so BC squared is A squared. So in conclusion, we found out that according to equation number 1, B squared equals to 64 plus A squared. We subtracted A squared from this equation, equation number 1, and found out that B squared minus A squared equals to 64. Here we have the trigonometric identity, that B, the algebraic identity, that B squared minus A squared equals to B plus A times B minus A. And according to equation number 1, B plus A times B minus A equals to 64. Here we know that BC equals to A according to our definition, and AC equals to B according to our definition. That is to say, and we know that BC and AC are integers, therefore A and B are integers. This is the first one, and the first thing. And the second thing, we also know that A and B are the lengths of the sides of a right triangle. That is to say, A and B as lengths, they must be positive numbers. So for 1 and 2, if we combine those two things together, we will conclude that a and b are positive integers. Okay? So if a and b are positive integers, it means that b plus a must be also a positive integer. And we know that b is the hypotenuse, it must be greater than the other side of the right triangle, that is to say b must be greater than a. We subtracted a from this equation and found out that b minus a is a positive number, but because of the fact that b is a positive integer and a is a positive integer, it means that if b minus a is a positive, it must be a positive integer. Because when you subtract or add two positive integers together, the result always must be a positive integer. Okay? Or if b is smaller than a, then it also could be a negative integer, but here we know that that is a positive, therefore b minus a must be positive integer. So we actually found out that b plus a is a positive integer and b minus a is also a positive integer. Okay? So what options we have? That when we multiply two positive integers by each other, the result is 64. We have very few options for such a scenario. So here, we have the column of b plus a. The first column is b plus a, and the second column is b minus a, and we will multiply those two positive integers together, and we'll get 64. Here, 1 times 64 is 64, 2 times 32 is also 64, 4 times 16, 8 times 8, 16 times 4, 32 times 2, and 64 times 1. In these all options, the result of the multiplication of two positive integers by each other, the result gives us 64. So we have in total 7 options. But because of the fact that we have already found out that b plus a must be greater than b minus a, it means that the first column must be greater, that is b plus a, must be greater than the second column, that is b minus a. So we will take only the options where the first column is greater than the second column. If 1 is not greater than 64, so we will cancel this option. 2 is not greater than 32, therefore we will cancel this option. 4 is not greater than 16, therefore we will cancel this option. 8 is not greater than 8, therefore we will cancel this solution. 16 is greater than 4, this is a good solution. 32 is greater than 2, therefore this is a good solution, the good option. And 64 is greater than 1, it is also a good option. Now we will add the two numbers together in order to find out what is the result of adding the two numbers together. So b plus a, we'll do the operation of b plus a plus b minus a. Okay, so if we add the two numbers together, the result is b plus b is 2b and a minus a is 0. So we found out that if we add the two numbers together, the result must be an even number. Why? Because 2b must be an even number. When b is positive integer, 2 times positive integer must be an even number. So we'll check the three options, and if we find out that the result of the adding the two numbers together is not an even number, we'll cancel the solution. Here 16 plus 4 is 20. 20 is an even number, therefore it is a good solution. 32 plus 2 is 34, that is an even number, it's also a good solution. And 64 plus 1 is not an even number, it is an odd number, therefore we cancel the solution. So we left only the two solutions that are possible. So we copy the two solutions here. According to the first solution, b plus a is 16 and b minus a is 4, and according to the second solution, b plus a is 32 while b minus a is 2. We'll focus on the first solution. So we will add the first equation to the second equation, and we get that b plus a is 2b, a minus a is 0, and in the other side of the equation we have 16 plus 4 is 20. So in conclusion we got that 2b equals to 20, we divided this equation by 2, and we found out that b equals to 20 over 2, that is 10. So b, the hypotenuse b of the right triangle ABC equals to 10 units, and we have the equation that b plus a equals to 16. So we subtracted b from this equation and found out that a equals to 16 minus b. But b is 10, so we can substitute b by 10, and we will get that a equals to 16 minus b, that is 10. So a is 16 minus 10, that is 6. So in conclusion, we found out that according to the first option, the value of a is 6 and the value of b is 10. Here, a equals to 6 units and b, the hypotenuse, equals to 10 units. Then we have the second option, that b plus a equals to 32 and b minus a equals to 2. We added those two equations together and found out that b plus b is 2b and a minus a is 0. So on this side of the equation we have 2b, and the other side of the equation we have 32 plus 2 is 34. So in conclusion, 2b equals to 34. We divided this equation by 2, and we found out that b equals to 34 over 2 is 17. So b equals to 17 units. When we have this equation that b plus a equals to 32, we subtracted b from this equation, and we found out that a equals to 32 minus b. But we already found out that b equals to 17, so we can substitute b by 17, and we got that a equals to 32 minus b, that is 17, so 32 minus 17 is 15. So we found out in conclusion that according to the second option, a equals to 15 units and b equals to 17 units. So I draw the two options here. According to the first option, it is given us the question that AB equals to 8 units. We found out that BC, that is actually A, equals to 6 units, and AC, that is B, the hypotenuse is 10 units. Inside this right triangle, we have this circle that is described by this specific right triangle, and we want to find out the radius of this circle that is described by triangle ABC. According to the second option, AB equals to 8 units, it is given us the question. BC is A, that is 15 units, and AC is B, that is 17 units. Okay, and here we have the right, this circle that is described by the right triangle, triangle ABC, and we want to find out the radius of this circle that is described by triangle ABC. So in order to find out the radius of those two circles, the radii of those two circles that are inscribed by the two right triangles, we will actually take triangle ABC, the right triangle, triangle ABC, that could be any triangle, and inside this right triangle ABC we have this circle. We'll find out the radius of this circle. In this way we'll get a formula that is true for any triangle, and we'll use this formula in order to find out the radius of those two, the radii of those two circles that inscribed by those two right triangles. Why we can use this formula in those two triangles? Because triangle ABC could be any triangle. And because of the fact that triangle ABC could be any triangle, we could use the formula, especially in those two triangles. Okay. So we defined side AB as A, side BC as B, and side AC, the hypotenuse, as C. Then we define the center of this circle as O. We define the point of tendency of tangent AB with this circle as N. We define the point of tendency of tangent BC with this circle as M. Then we join points O and N together by a straight line. Point O is the center of the circle, point N is the point of the circle itself. Therefore, ON is the radius of this circle, that is equal to capital R according to our definition. Then we have rule number 1, that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here, radius ON, it is drawn to the point of tendency. That is to say, it is drawn to point N, that is the point of tendency of tangent AB, with this circle, and whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO, according to rule number 1. So if AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule number 1. Likewise, we have the radius OM that is drawn to the point of tendency, therefore, according to rule number 1, tangent BC will be perpendicular to the radius MO. So if BC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule number 1. So in quadrilateral ONBM, we have 1, 2, 3 right angles, and the sum of 3 right angles is 90 times 3 is 270 degrees, plus the fourth angle, that is actually angle NOM. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. We subtracted 270 degrees from this equation, and we found out that the missing angle NOM equals to 90 degrees. So the missing angle is equals to 90 degrees. So clearly, quadrilateral NOBM, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral NOBM as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, NO equals to BM. So NO equals to BM. But we already found out that NO equals to R, and it equals also to BM. Therefore, BM also equals to R. Likewise, according to the rule that the opposite sides of rectangle are equal to each other, we get that NB equals to OM. NB equals to OM from one side, but we already found out that OM equals to R. Therefore, NB must be also equal to R. So, in conclusion, we found out all the sides of quadrilateral NOBM are equal to each other, they are equal to capital R. Therefore, quadrilateral NOBM, it is not a rectangle but a square. Then we found out the length of line segment AN. AN equals to AB minus NB. AB is A, NB is R, so AN equals to A minus R. Here we found out the length of line segment MC. From the drawing, it is very easy to see that MC equals to BC minus BM. BC is B, BM is R, so MC equals to B minus R. So in conclusion, AN equals to A minus R and MC equals to B minus R. Then I presented to you rule number 2 that the lengths of two tangents from a common standpoint to a circle are equal. So if we focus on the common standpoint point A, we have two tangents to the circle, tangent AN and tangent AL. And according to rule number 2, they are equal to each other. That is to say, AN equals to AL. If AN equals to AL, but we also know that AN equals to A minus 4 and AL equals to AN. Therefore, AL also equals to A minus 4. Okay? Then we focus on the common standpoint point C. According to rule number 2, we have two tangents to this circle. From point C, we have tangent CL and tangent CM. And according to rule number 2, they are equal to each other. That is to say, CL equals to CM. But we have already found out that CM equals to B minus R, and it is also equals to CL. Therefore, CL also equals to B minus R. So in conclusion, we found out that CL equals to B minus R and AN equals to A minus R. So what is the length of the hypotenuse AC? The hypotenuse AC, it is equal to AL plus LC. AC equals to AL plus LC. AL equals to A minus R and LC equals to B minus R. So we substitute AL by A minus R and LC by B minus R. And we also, according to our definition, the hypotenuse AC equals to C, so we substitute the hypotenuse AC by C. In conclusion, we found out that C equals to A minus R plus B minus R. So C equals to A minus R, to A plus B, minus R plus minus R is minus 2R. So in conclusion, C equals to A plus B minus 2R. We added 2R to this equation and found out that 2R plus C equals to A plus B. We subtracted C from this equation and found out that 2R equals to A plus B minus C. We divided this equation by 2 and we found out that the radius of this circle that is described by the right triangle ABC equals to A plus B minus C over 2. So because of the fact that triangle ABC could be any triangle, we can implement this formula in our two triangles that are right triangles, of course. So this formula is good for any right triangle. Therefore, we can implement the new formula in our triangles, two triangles that are right triangles. So the formula is r equals to a plus b, that is the sum of its perpendiculars, minus c, that is the hypotenuse, over 2. So a plus b here is 8 plus 6, that is 14, minus c, that is 10. So 10 plus 6 is 14, and 14 minus the hypotenuse, that is 10. 14 minus 10 is 4, and 4 over 2 is 2. So in conclusion, we found out that the radius of this circle that is described by the right triangle, this specific right triangle, triangle ABC, equals to 2 units. Then we have the second solution here. We have the second right triangle. We used the same formula to find out the radius of this triangle, because this formula is true for any right triangle, and especially for this right triangle. The radius of this circle will be equal, according to this formula, to the sum of its perpendiculars, that is 8 plus 15 is 23, and 23 minus the hypotenuse, that is 17. 23 minus 17 is 6, and 6 over 2 is 3. So in conclusion, the radius of this circle is 3 units, and the radius of this circle is 2 units. So actually we found out that we have two solutions to the question. Here, the radius of this circle that is described by this specific right triangle, triangle ABC, could be equal to either 2 units or to 3 units. We finished with the first question, then I presented to you the second question, and we solved the second question in 2 different methods. According to the first method, we have here a quarter circle, side OB equals to 2 units, AD equals to DO. Inside this quarter circle, we have the light blue triangle, triangle DCB, and we want to find out the area of this light blue triangle, triangle DCB. So first of all, because of the fact that AOB is a quarter circle, this angle equals to 90 degrees, point O is the center of the quarter circle, OB is the radius of the quarter circle, it is equal to 2 units, therefore AO is also the radius of the quarter circle, that is also equal to 2 units. So here we know that AO equals to AD plus DO. Here AO equals to AD plus DO, you can see it from the drawing. If AD equals to X, then DO must be also equal to X, because they are equal to each other. So here we have X plus X, that is equal to AD plus DO, that is equal to AO, and AO equals to OB, because both of them are the radii of the quarter circle. Here they are the radius, and the radius equals to 2 units according to what is given us the question. So from this following equation, we get that X plus X equals to 2. That is to say, 2x equals to 2. We divided this equation by 2 and found out that X equals to 1 unit. Here AD that is equals to X equals to 1 unit, and DO that is also equals to X equals to 1 unit. Okay, then we actually completed the quarter circle to a semicircle, completed the quarter circle to a circle, and here point O is the center of the circle, point P is the point on the circle itself, therefore OP is the radius of the circle, that is equal to 2 units. Then we extended side CD by straight line until it touches the circle, and we don't know where we touch the circle, so we assumed that side CD will touch the circle at point X, not at point P. So we created here angle BCX. I deleted here. We have here angle BCX, that is absolutely a peripheral angle, but this peripheral angle BCX, that is equal to 90 degrees, doesn't rest on the diameter of this circle, that is PB. Why PB is the diameter of this circle? Because it is a straight line that passes through point O, that is the center of the circle, therefore PO is the diameter, therefore PB is the diameter of the circle. So we have here peripheral angle BCX that is equal to 90 degrees according to what is given as the equation, and peripheral angle BCX that is equal to 90 degrees does it rest on the diameter of this circle that is PB. And we know that any peripheral angle that is equal to 90 degrees must rest on the diameter. So we got a contradiction. So peripheral angle BCX must rest on the diameter, and it doesn't rest on the diameter. So in order to avoid this contradiction, we must conclude that point X merge with point P. And in this way we created peripheral angle BCP that is equals to 90 degrees, and it does rest on the diameter of this circle that is PB. In this way we solved the contradiction. We have here peripheral angle PCB, BCP that is equal to 90 degrees, and it rests on the diameter that is PB. Okay, so here we know that PB is a diameter equals to 90 degrees, and we have the rule that so it is PB is a diameter, and it's a diameter, it must be a straight line, of course, and we know that the sum of the angles from one side of a straight line must equal to 180 degrees. So if we focus on the upper side of the straight line PB at point O, the sum of the angles here must be equal to 90 degrees. So this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees. Also, in order to complete the sum of the angles here to 180 degrees, this angle must be equal to 90 degrees. So we found out that in triangle POD this angle equals to 90 degrees, therefore it is a right triangle. We implemented the Pythagoras theorem of the right triangle POD in order to find out the hypotenuse PD. According to the Pythagoras theorem of the right triangle POD, PD square equals to DO square plus BO square. So PD square equals to DO square, DO is 1, so DO square is 1 square, that is 1, plus PD square, plus PO square. PO is 2, so PO square is 2 square, that is 4. So in conclusion, we found out that PD square equals to 1 plus 4, that is 5. We took out of this equation and found out that the hypotenuse PD equals to square root of 5 units. We repeated the same process on this right triangle, triangle DOB. In the right triangle, triangle DOB, the square of the hypotenuse equals to the sum of the circles of the perpendiculars, that is to say DB square equals to OB square plus DO square. Repeat again, the right triangle DOB, PB square equals to DO square plus OB square, so DB square equals to DO square. DO is 1, so DO square is 1 square, that is 1, plus OB square, OB is 2, so OB square is 2 square, that is 4. So in conclusion, we found that DB square equals to 1 plus 4, that is 5. We took out of this equation and found out that DB equals to the square root of 5 units. The hypotenuse DB equals to the square root of 5 units. Then we extended the radius AO by a straight line until it touches the circle at this point, point Z. Point Z is the touching point of the extended AO in this circle. Then we implemented rule number 1 on this drawing. Here, rule number 1 states is if chord AB intersects with chord CD at point O, then AO times OB equals to CO over OD. Again, AO times OB equals to CO times OD. We can implement rule number 1 in our drawing, because in our drawing we have chord AZ that intersects with chord CP at point D. Therefore, according to rule number 1, we get that AD times DZ equals to CD times DP. Again, chord AZ intersects with chord CP at point D, therefore AD times DZ equals to CD times DP. According to rule number 1, of course, AD is 1. Here, DZ is 1 plus 2, that is 3. And CD is the missing line segment, so we leave it as it is. And DP equals to the square root of 5 units. So in conclusion, we found out that 3 equals to CD times square root of 5 units. We divided this equation by square root of 5 units, and we found out that CD equals to 3 over square root of 5 units. Yes, CD equals to 3 over square root of 5 units. We implemented the Pythagoras theorem of the right blue triangle, triangle DCB. According to the Pythagoras theorem, DB square equals to DC square plus CB square. The right triangle, triangle DCB, DB square equals to CD square plus CB square. DB equals to the square root of 5, so DB square is square root of 5 squared, that is 5. Here, CD is 3 over 5, so CD square is 9 over, CD is 3 over square root of 5, therefore CD square is 9 over 5. So CD square is 9 over 5 plus CB square, that is missing 9 segment. So we found out that 5 equals to 9 over 5 plus CB square. We subtracted 9/5 from this equation and found out that 5 minus 9/5 equals to CB square. We multiplied 5 by 5 and then we divided by 5 in order to have a common factor with this expression. We found out that 25 minus 9, 5 times 5 is 25, so 25 minus 9 is 16. So we have here in this side of the equation 16 over 5, that is equal to CB square. We took a root out of this equation and found out that the length of the missing line segment CB equals to the square root of 16, that is 4, over square root of 5. So here we found out that CB equals to 4 over square root of 5. Now it is very easy to find out the area of this right blue triangle, triangle DCB. It will be equal to the base of the triangle, that is DC, times the height of the base, that is CB, over 2. Repeat again, the area of triangle BCD, blue right triangle, will be equal to the base of the triangle, that is DC, times the height of the base, that is CB, over 2. DC equals to 3 over square root of 5, CB equals to 4 over square root of 5, all divided by 2. Here in the numerator we have 3 times 4, that is 12. In the denominator we have square root of 5 times square root of 5, that is 5, times 2. 12 over 2 is 6, so in the numerator we left only with 6. In the denominator we left only with 5. So in conclusion, we found out that the area of the right blue triangle, triangle DCB, equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. We finished with the first method, then I presented to you how to find out the area of the blue right triangle, triangle DCB, according to the second method. Here we have already found out in the first method that the angle AOB equals to 90 degrees, AD equals to 1 unit, DO equals to 1 unit. Here we completed, and O of course in the center of the quarter circle, we completed the quarter circle to a semicircle. Then we extended the radius BO. We know that BO is the radius from the first method. We extended the radius BO by straight line until it touches the circle. At this point, we define the touching point of the extended BO in the semicircle as point P. Then we extended CD we extended side CD of the right triangle DCB by a straight line until it touches the circle at point P. And we know that when we extend side CD by straight line, it must touch the circle at point P and only at point P. We have already proved it in the first method. So when we extend the straight line, the side CD by straight line, it will touch the circle at point P and only at point P. According to the first rule, according to the first method, this angle equals to 90 degrees. We define this angle as theta. So if this angle equals to theta, this angle equals to 90 degrees, this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in this right triangle DOP to 180 degrees. This angle must be equal to 90 degrees minus theta, because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. The same rule is true in the right triangle PCB. This angle equals to theta, this angle equals to 90 degrees, so this angle must be equal to 90 degrees minus theta exactly for the same reason. Then we proved that that the right triangle POD is similar to the right big triangle, triangle PCB. why those two right triangles are similar to each other? First of all, those two angles are equal to each other. Those two angles are equal to 90 degrees. Both of them are equal to 90 degrees, therefore they are equal to each other. Those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. And this angle is a common angle that belongs to both triangles, so this angle equals to itself. We actually proved that all the angles of triangle, the big right triangle PCB can go into all the angles of the small right triangle PDO. Therefore, those two right triangles are similar to each other according to angle similarity rule. Triangle POB is similar to triangle PCB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that PD over PB equals to DO over CB. It also equals to PO over PC. Repeat again. PD over PB equals to DO over CB equals to PO over PC. PD equals to 5 units. PB equals to 2 plus 2, that is 4. DO equals to 1, and CB is the missing line segment. So we leave it as it is. PO equals to 2, and PC equals to square root of 5 plus DC. Here PC equals to square root of 5 plus DC. So from this long equation, we derive the first equation, that square root of 5 over 4 equals to 1 over CB. Because multiplied this equation and found out that square root of 5 times CB equals to 4. We divided this equation number 1 by square root of 5, and we found out that the missing line segment CB, here, line segment CB equals to 4 over square root of 5 units. Then we implemented the Pythagoras theorem on this right blue triangle CBD. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say, the hypotenuse is dB, so dB square equals to dc square plus cb square. dB square equals to dc square plus cb square. dB equals to square root of 5, so dB square is square root of 5 squared, that is 5, plus dc square. dc equals to 3 over square root of 5, so dc square is 9 over 5. 9 over 5. So here, we have actually the missing line segment here. We have already found out that actually DC is the missing side. So here BD equals to the square root of 5, so BD square is 5. BC is the missing line segment, so we leave it here. DC is the missing line segment, so we leave it as it is. And here we found out that CB, we already found out that CB equals to 4 over square root of 5, so therefore CB square will be equal to 16 over 5. Okay, CB square is 16 over 5, so in conclusion we found out that 5 equals to DC square plus 16 over 5. This is the missing line segment. We subtracted 16 fifths from this equation and found out that 5 minus 16 fifths is 5 minus 16 fifths equals to DC square. Here we multiplied 5 by 5 and then we divided by 5 in order to have a common factor with this expression. 5 times 5 is 25, so in the numerator we have 25 minus 16. In the denominator we have 5, so 25 minus 16 is 9, so it is 9 over 5, that is equal to DC square. We took a root out of this equation and found out that DC, the missing line segment DC, equals to the square root of 9, that is 3, over square root of 5. So here DC equals to 3 over square root of 5. Now it is very easy to find out the area of this right blue triangle, triangle DCB. The area will be equal to the base of the triangle, that is DC, times the height of the base, that is CB, over 2. The area of the right blue triangle DCB equals to the base, that is DC, times the height of the base, that is CB, over 2. DC equals to 3 over square root of 5 units. CB equals to 4 over square root of 5 units, all divided by 2. In the numerator we have 3 times 4, that is 12. In the denominator we have square root of 5 times square root of 5, that is 5, times 2. So here 12 over 2 is 6, so in the numerator we left only with 6, and the denominator we left only with 5. So in conclusion we found out that in both methods the area of the blue right triangle triangle DCB equals to either 6 over 5 square units, or in terms of numbers, it is equal to 1.2 square units. Okay? Thank you very much.